Hello viewers, welcome to you Autonomous Colors. Today we are going to discuss about a new concept of theory of computation. Now we can focus on the slide. Today we are going to discuss about the concept of that is known as how to eliminating epsilon transitions in our theory of computation. That means in NFA we have some epsilon transitions. From that NFA we need to remove these epsilon transitions. So today we are going to discuss about what are the different outlines about that topic, like what are the real use of that epsilon used in our transitions part. So today discussing about the introduction, then we are learning what are the different examples are related to our this eliminating epsilon transition part. So first of all we know that in the case of NFA with epsilon can be converted to NFA, that means without any epsilon. We know that epsilon is known as a one type of empty transition flow. So we need to remove this epsilon from our transition diagram. In that moment this NFA without epsilon can be converted to DFA. So that if a transition must contain epsilon, then you cannot say it is known as a DFA. If a user want to make NFA to DFA, we must to remove the cause of epsilon transition. So that it is the most important part through which you can easily remove epsilon from NFA diagram. So here to do this we will use a method which can remove all the epsilon transition from the given NFA part. So here we have some methods which I described in below. Find out all the epsilon transitions from each state from Q, that will be called as epsilon closure. If a user want to find out how to remove that epsilon from their transition diagram, in that moment we should know about it, how to create a closure of that epsilon. That means here we are going to discuss about the epsilon closure property. That means the epsilon closure of Q1 where Qi is belongs to capital Q. Here the capital Q is a set of states and that set of states are created through this epsilon closure property. So here then the epsilon dash means just we can say it is the inverse transitions can be obtained where the transition inverse mean a epsilon closure on transition moves. So we can going to repeat the step 2 for each input symbol and each state of given NFA part. So that if a user want to create a state, in that moment a user must to invoke this step 2 more than one times. Whenever user can invoke this step more than one times, then it can create some synchronous steps in our transition table or transition diagram. So if a user must to invoke it repeatedly step 2, then we are getting some consequence at the time of transition table formation. Here also we have step 4. In that step 4 we are using the resultant states. Here the resultant states where the transition table for equivalent NFA without epsilon can be built. That means if a user want to design a transition table, in that moment in that transition table we never contain any type of epsilon input symbol. Without epsilon we can create some states, that may be empty state, that may be anything else. There is no any state. That means if a state does not contain a next state, in that moment we are giving here that is known as phi set. That means the phi set is a part of here which is used as a one non-empty state. So that it is a general way through which you can be describe just how to remove epsilon from our transition table which is belongs to NFA part. Similarly, without knowing this elimination, a user never convert that NFA to DFA part. First of all, user required to remove epsilon from NFA, then that NFA must be converted to DFA. It is a general procedure. So without that procedure, user never do anything else. So that if a user want to describe this concept through an example which is present in this slide, here we can focus on it. So in this slide already we are converting the following NFA with epsilon, means is known as an empty flow, to NFA without epsilon. That means we have a diagram and that diagram is known as a NFA with epsilon because this is known as a epsilon symbol. So we need to remove that epsilon symbol from this diagram. So if a user want to remove this epsilon symbol from this diagram, a user must follow NFA without epsilon. If a user want to design NFA epsilon, in that moment we must follow some procedures which is already described in below. In the solution part, first of all user need to take some epsilon closure properties. What are the different epsilon closure properties which are described in this slide? Here we will first obtain epsilon closures of Q0, because the above diagram we have 3 states, and that is known as a Q0, Q1, then Q2. Here Q0 is known as initial state, Q1 is known as a one next level state, and Q2 here is known as final state. So in that 3 number of states, from that 3 number of states must be implemented through epsilon closure property. If you take that epsilon closure of Q0, in that moment, if epsilon means nothing else, whenever user can put epsilon in Q0 state, then we are getting the same state, that is known as Q0, which is described in this slide. If a user want to take the epsilon closure property on state Q1, in that moment we are getting 2 state, one state named as a Q1 itself, another known as a Q2, which is already described in this diagram. Whenever user can put epsilon symbol to Q1 state, in that moment we are getting a next state which is known as a final state, that is known as Q2, which is already focused in this slide. So the epsilon closure property, which is part of that Q2, in that moment you are getting same state, because we know that whenever a state can contain epsilon means which is denoted as itself, that means there is no any transitions happen. If any transitions happen due to epsilon, then we can write the state which already described in this diagram, which is known as the Q2. Whenever Q1 take the epsilon, then it can create a next state that is named as Q2, and here that Q2 is known as a final state. So the next part we have, now the epsilon dash transition, we can say it is a inverse transition on each input symbol is obtained as if inverse transition of Q0 comma A. That means we are using a state Q0 with input symbol A. In that moment we are going to describe its epsilon closure properties. In that moment we can take it epsilon closure of transition of, that is known as a transition which is taken through Q0 then epsilon. First of all you can take the Q0 epsilon. In that moment we comma A, then we can close that parenthesis, then we can also written here, we can expand it, then we are writing here epsilon closure, then we are writing the transition. In that transition we can expose that that is known as a transition of Q0 epsilon to in these properties, which is already mentioned here, that is known as epsilon closure of Q0. That means whenever user can put this section, it is automatically follow up that part, that is known as epsilon closure with Q0 and comma A. Simultaneously it will be converted or explained or described through next step, that is known as epsilon closure of transition Q0. That means epsilon closure Q0 is already mentioned in the previous part, or we can say the top of this slide, that is known as epsilon closure of Q0 is known as Q0. That means this epsilon closure of Q0 we can writing here Q0 comma A. Whenever user can write this statement, similarly if we would say that in next step, that is known as the epsilon closure in the transition of Q0A, we can say that the transition of Q0A, that means whenever user can put input symbol A to Q0 state, then automatically forwarded to Q1, which is already mentioned here. That means whenever user can input A to Q0 state, in that moment we can get a transition state that is known as Q1. Whenever user can getting the closure property of epsilon closure property of Q1, in that moment we are getting Q1 comma Q2, which is already mentioned in the previous part. Okay. Next we are going to discuss how to take the, already in the previous part we are taking the input symbol as B, but here we are taking the input symbol as A, and in that part, the previous part already A and this part is known as B. Whenever user can put B input symbol to same Q0 state, in that moment we are going to calculate its state calculation, or you can say epsilon closure calculation. In that moment you can putting your same procedure epsilon closure, then transition, then the transition of Q0 epsilon, then comma B. Whenever that transition of Q0 epsilon, that is known as the epsilon closure of Q0, whenever user can put that is known as epsilon to Q0, it is getting the same state, that is Q0 epsilon Q0 property, then comma B. In the last third step we are getting the epsilon closure of transition Q0 comma B, because you know that is epsilon closure of q0, that is same q0 which is already mentioned here. Then finally we are getting B input symbol, which is apply in your q0, but in the previous diagram which is already mentioned here, that is known as q0. A q0 only contain accept a input symbol like A, it is never accept a input symbol like B. Whenever user never accept input symbol like B, in that moment we are getting, that is known as a phi set. That means there is no set is created, that means it is denoted as phi means there is non-exist state, there is no next state is created due to q0 accepting a input symbol like B. Similarly, in next state, that is known as a q1, in that q1 state we can also put a input symbol A, simultaneously input symbol B. Similarly, whenever user can put this way of movements, then we can create here transition inverse of q1 comma A, then we are getting a properties like epsilon closure of, that is known as transition into transition of q1 epsilon then comma A. That means the transition of q1 epsilon, which is a part of epsilon closure of q1 then comma A. We know that epsilon closure of q1 getting the two state, that is known as q1 q2 then comma A. That means the transition of q1 q2 both are taking input symbol like A. So here the epsilon closure of transition q1 A, then union of q transition of q2 A. Whenever user can put input symbol like A to q1 state, in that moment we are never getting any state, next state, that means it is denoted as phi. Similarly, whenever user can put A to q2 state, then there is no any movements or there is no any new state is created, that's why it is denoted as same phi. The phi, it is a part of that which is denoted as a non-exist state. Then we can going to find out its closure property, epsilon closure property. The epsilon closure of phi union phi means same phi state, there is no state is being created whenever user can put q1 with input symbol, that is known as A. Similarly, user can put the input symbol like B to state q1, in that moment we are going to find out its epsilon closure properties like epsilon closure of transition into transition of q1 epsilon then comma B. In that moment here the transition of q1 epsilon, we are getting the epsilon closure of q1 then comma B. Then we are going to calculate this transition. In that transition state we are already mentioned here. So here the transition of epsilon closure q1 getting the two state, that is known as q1 q2 with accepting a input symbol like B. Similarly, that transition of q1 q2 can be divided into two parts, and that part must be explained through this statement like epsilon closure of transition q1 B union then transition of q2 B. In that moment we are going to calculate what are the transition result of q whenever that state q1 accepting a input symbol B. That means whenever user can put B symbol to q1, there is no state is being created, that means it is known as a phi set, and that phi set must be union with another way of transition which is explained in this section, like whenever user can put q2 with input symbol like B, in that moment we are getting a parameter or state that is known as q2. That means we are comparing the phi union q2, in that moment we are creating a q2 state. Here the q2 state is being created and it is mentioned here epsilon closure of phi union q2. In that moment that q2 state is being created. So it is a general way of explanation which is already described in this transition state. So it is an explanation through which you can be design another way of explanation, that is known as how to take that q2 with a epsilon transition, and we are going to find out its moments. Okay, here the epsilon, just we can say it is need to remove from the transition table. We need to create a transition state that is known as transition inverse on q2 is obtained as the transition inverse of q2 with accepting a input symbol like A. In that moment we are going to calculate this epsilon closure property. In that closure property we are going to enlarge it, just we can say transition of transition q2 whenever accepting a state that is known as epsilon. In that moment we are getting epsilon closure q2 which is already mentioned in the previous section. So here that epsilon closure q2 must be opened or described whenever it can be explained or described, it can create a state named as Q2. That means the epsilon closure of Q2 is known as Q2, which is already described in the previous slide. So here that Q2 must take a input symbol like A. Just to, it is one type of just we can say it is an explanation. One expression must be enlarged, or we can say elaborately described to another statement. So here that epsilon closure of Q2 can create a state which is named as Q2, and with a parameter or we can say that is known as the input symbol, that is known as A. So in this way we are generally creating that state formation, but somehow it will be related to our NFA part, which is already mentioned here. If a user want to calculate the epsilon closure of transition Q2 comma QA, just we can say that Q2 can accepting a input symbol like A. In that moment there is no any transitions happen. That means there is no any transition state created in their transition diagram. That means it is known as empty in nature. That's why I mentioned here phi. Phi is a state, and that phi state it is known as the empty state. In that empty state must be created whenever it can put a input symbol to state Q2. Similarly, if a epsilon closure, we can say that is known as a phi set. Whenever user can put an input symbol A to Q2 state, in that moment we can create a state that is known as a phi state. There is no a new state is being created. So that if a user want to going to calculate the epsilon closure of phi set, in that moment we can getting a state that is named as a phi. That means there is no new state is being created here. So similarly, whenever user want to put the input symbol B to same state that is known as a Q2, in that moment it is mentioned here that is known as a delta dash. Delta dash, it is a part of a, that is just we can say the removing transition way of some epsilon in our transition diagram. So here that epsilon closure part must be contain some parameter like transition of transition, that is known as a Q2 of epsilon. Whenever that Q2 can contain epsilon, in that moment the same epsilon closure Q2 we can be elaborate in this way. So here whenever user can describe that epsilon closure with Q2 accepting a parameter like B, and we are going to calculate the overall transition moment. In that moment here the epsilon closure of transition, that epsilon closure Q2 must be contain same state. There is no a new state is being created. In that moment we can create a state named as the Q2. Similarly, that Q2 must accepting a input state, or we can say input symbol, that is known as B. Whenever a there is need to make a transition in between the Q2, and that Q2 can accept a state named as, or we can say input symbol named as B. In that moment we are going to calculate is epsilon closure part. Whenever user can put this way of statement like epsilon closure of transition of Q2 comma B, then we can create a state that is named as Q2. That Q2 is created due to this transition part. So here we are going to calculate this epsilon closure of Q2. If a user want to create the epsilon closure of Q2, in that moment finally we are getting a state named as same Q2 state. So it is a general way of movement. Next we are going to discuss now where we will summarize all the computed transition dash, or you can say transition inverse sections here. So finally the transition inverse Q0A we are getting the state named as the Q0 Q1. Similarly the transition inverse of Q0B, it can create a state named as a phi. Similarly the transition inverse of Q1 can input a input symbol like A, we can create a phi state. And next we are getting a input symbol that is known as B to Q1 with transition inverse, that is created Q2 state. And that is the transition inverse of Q2 can accept a input symbol like A. In that moment we are getting a phi state, that means there is no new state is being created. That is a simultaneously we can say that the transition inverse of Q2 accepting a input symbol like B, then it can create a state named as Q2. So it is a general way of state transition table movements. So we need to put this way of explanation to a transition table. Whenever user want to design a transition table, in that moment we can take three column here. First known as a state, second one known as the first input symbol that is A, second input symbol B. Whenever user can put Q0 as a initial state, and it can input a that is known as a as a input parameter, we can say we can getting a state named as q1, q2. Whenever user can put a input symbol a, you can getting q1 or q2. Just we can say whenever user can put any type of symbol, just we can say, which is already mentioned in their diagram, but somehow we can write here there is no q0, or we can say q1, which is already mentioned in that part. So we are getting the epsilon whenever user can accept a b parameter to q0, then we are getting 5. Then whenever user can take two final state, that is named as a q1 and q2, because you know that here that q2 is known as a final state, but somehow that q1 can take the input symbol b, it can create a q2. That means due to that reason we are creating two final state. We know that NFA can accept two final state, there is no problem, but here all type of final states must be denoted through star mark. Then that q1 star, we are getting the 5 input parameter. Then that b, whenever that q1 can accept a input symbol like b, then it can create a state named as q2. Similarly, that q2 is known as a final state, we can put an input symbol like a, then we are getting the 5, there is no new state is being created. Whenever user can put that is input symbol like b, then it can create a state named as, that is known as state b. So it is a general way of movements through which you can be created. So if a user want to design this overall process, we need to make an formation which is already explained in this slide. Here the state q1 and q2 become the final state as epsilon closure of q1 and q2, which contain the final state that is known as q2. So the NFA can be shown by the following transition diagram. The next slide already were mentioned that if a user want to explain it, the state q1 and q2 become the final state as epsilon closure of q1 and q2, contain the final state that is known as the q2. Here the NFA can be shown by following transition diagram. Now we are designing this transition diagram from that statement here. So in that statement already that q0 can accepting a, that is known as the input symbol like a, in that moment it can create a state named as a q1. Whenever that q0 same accepting a input symbol like a, then it is automatically linked with a state named as a q2, and both q and q2 is denoted as a final state. All type of final state are always denoted through double rounded circle. Similarly, that q1 can accept a state, or you can say input symbol like b, it is linked with q2 state, and that here that q2 is known as a final state. Whenever that q2 can accept a input symbol like b, then it is automatically self redirected. So it is a self redirected state that is known as q2, but here that q2 is never accept any other input symbol like a. If there is no any other symbol like a, that means it is formation of the phi set. All type of phi state it is not required to show in that diagram, it is optional in nature. If a user want to display this type of phi set in this transition diagram, that is which is just denoted without any epsilon, so that in that transition diagram there is no need to mention any type of phi sets in this diagram. So it is a way of explanation through which you can be explained, so that if a user really want to make a transition movement, in that moment there is no any new transition is being created. If a user can getting this transition diagram, and that transition diagram helps to make it more reliable and successful way of movements, that means it is a way of transitions. In that way of transitions we are getting a full of transition diagram without any epsilon properties. If a user want creating a epsilon without any mentioning this transition diagram, that means here we are getting a NFA, that NFA is already created without any epsilon part. So if this diagram is created, then we are getting a chance to convert this without epsilon transition NFA must be converted to DFA part, which is already discussed in your next session or next class. So finally, if a user want to mention any type of requirements in that transition diagram, in that moment we must to take the steps. We have the 4 steps. By using that 4 steps we can easily remove epsilon from their NFA part. Okay, finally thank you. If you have any doubt you can send query through our YouTube channel. Have a nice day.